If I'm trying to measure something with a sensor, so for example, this circuit right here is the temperature sensing circuit that you've used in your lab in the past. You have a resistive temperature sensor, a thermistor, hooked up in a voltage divider circuit. But this is true with any sensor, honestly. One of the things that I'd like to ensure is the case is that in this case, the voltage here, what I'm trying to measure, this voltage here is going to stay the same before I hook up whatever I'm using to measure it, whether it's a voltmeter, an analog to digital converter, etc. It's going to stay the same both before I hook that up and after I've hooked that up. Another way to say that is in an ideal world, the act of taking a measurement will not affect the variable being measured. But that's an ideal case. And so we can define a loading error, EL, as the difference between the measurand and the indicated value of measurement. So basically my V out before I've added the ADC to this and after I've added the ADC. But this is not just limited to voltages. If I stick a thermometer in some water, there's going to be some energy transfer there, and the temperature of the water is going to change, perhaps very slightly, but it's going to change, right? So just by the act of taking the measurement, I am changing the value that I'm trying to measure. And that's what loading error is trying to quantify. Let's look at a really simple example of this. In this case, I have some sensor, right? This entire block here indicated by some voltage output that's coming out of my sensor. And maybe this is a sensor hooked into an interface circuit. It doesn't really matter. But I have some voltage output from this sensor along with some impedance associated with this sensor, an output impedance with this sensor. But I can effectively model as this, a voltage source with a resistance. Now I want to hook up a voltmeter to actually measure the value of that sensor. So I'd go from the positive side of my voltmeter to that node, and the negative side of the voltmeter to that node. And in an ideal world, this voltmeter has an infinite input impedance. But in fact, it's going to look something more like this, where it has some resistance between those terminals. So let's call that RVM for now. So I can redraw this circuit like this. And ideally, I'd like to be measuring V sensor when I measure this sensor over here, right? That's the voltage that I expect to get out of this sensor. But in fact, what I've done by hooking up this non-ideal voltmeter to the circuit is I've created a voltage divider here. So this is the new output that I'm actually measuring. So I'm going to call that VO. And VO is going to equal that voltmeter impedance divided by R0 plus a voltmeter impedance times that whole quantity times V sensor, right? And if this voltmeter impedance is really high relative to R0, right, this effectively becomes 1 and V out equals V sensor, which is what I want, right? Now the challenge comes when the output impedance of my sensor is on the same order of magnitude as the voltmeter input impedance. Or if I need a really precise or really accurate measurement, right, it can even be a problem if it's just somewhere in the ballpark. Right? So in general, I want my voltmeter impedance, these input impedance of the measurement circuit, or that could be an analog to digital converter as well, I want that to be really high. So high input impedance, low output impedance from my sensor. And that'll give me the sensed voltage that I want to sense. Effectively a low loading error, right? I'm not loading down that voltage with this extra impedance. For a more complex example, let's go back to that thermistor circuit. And now I'm hooking up a voltmeter to that and trying to measure this V out here. And my ideal case, I'm going to get a V out that is based on just this resistor divider circuit. So I'd have RT over RT plus R0 times Vn, where RT is my thermistor value and R0 is the other resistor in my voltage divider. In reality, I now have two resistors in parallel down here, right? So if I compute what V out is in reality, I'm going to have an equivalent resistance for these two resistors in parallel, or I could rewrite that as Rm in parallel with RT over Rm parallel with RT plus R naught, that whole thing times Vn. Now, Rm in parallel with RT is going to be equivalent to Rm times RT over the sum of those. That's just from your basic circuits. And so if I substitute that back in here, that simplifies to this term down here, where I effectively have what I had for the ideal, RT over RT plus R naught times VI, RT over RT plus R naught. But then I also have this extra term here in my denominator, this R naught RT divided by Rm. And so what that's telling me is if Rm is very large, then my loading error is going to be very small. And similarly, if Rm is on the order of R naught or RT, or somewhere in between those, it's actually going to affect the value of my output voltage. So as Rm goes to infinity, I'm going to the ideal case, which is what I expect. And we could, of course, calculate that loading error. If I call this V out in the ideal case, and this one out here, V out in my real case, then my loading error would be V out in the ideal case minus V out in the real case. Right? And so this would give me some voltage loading error in my output. So if I plug actual numbers into this for the resistances, I can get some sense of what that loading error might be. So if I want to solve this loading problem, really what I need for whatever touches my sensing circuit, whatever is providing that interface, I'm going to need it to have a really high, approximating infinite input impedance. In that way, I don't load down that voltage or whatever it is I'm trying to actually measure here. And so in order to do that, I'm going to use things like op amps, and op amps configured as unity gain buffers, and those are going to be providing very, very high input impedances so that I don't have to worry about a voltmeter and an analog digital converter actually loading this down.